Hello everyone. In this video, we are going to look at chapter 17, section 17.5. In addition from the previous video and section that we talk about rotating objects, this one we're going to add into the frictional rolling problems. We know that if a lot of times the rigid body are in general plane motion, which is a combination of translational motion and rotational motion. So being said, we usually have these three equations in general. Fx on the horizontal direction equals magx, and on the vertical direction you have Fy equals magy, and also you have the rotational mg equals ig alpha. Sometimes it will be convenient to write the moment equation about the point P rather than the G. So the last equation becomes sigma MP equals sigma MKP, where this sigma MKP represents the sum of the moment of IG alpha, MA, and MAG about point P. So equations of motion here, when analyzing the rolling moment of wheels, cylinders, or discs, it may be known if the body rolls without slipping or if it slips or slides as it rolls. So for example, consider the disc with the mass m and the radius subject to the known force P. Then the equation, so we horizontally you have P pulling minus F equals mag, and then vertically you have normal force going up, weight coming down equal to zero. Vertically, we don't have any movement, right? So horizontally is the P minus F equals mag. Now, for the rotational, mg equals ig alpha, or m times r equals ig alpha. There are four unknowns here. We only have three equations here, and that's why we need the additional equation here to help us solve the problem. The fourth equation can be obtained from the slip or non-slip condition of the disk. We're going to make two different assumptions, assuming no slipping. If no slipping, we can use this equation Ag equals alpha r as the fourth equation if no slipping. And do not use friction, lowercase f, friction equals mu s n. Do not use that if no slipping. After solving it, we need that one additional step to verify if our assumption is correct by checking how is the friction force relating to mu s times n. If it's less than equal to, then yes, it's correct. Your assumption is correct. Now, another way would be assuming it is slipping. So you have friction force F with lower f equals mu k in kinetic friction coefficient times the normal force as the fourth equation if we're slipping. And in this case, Ag does not equal to alpha r. Okay, so two different conditions. Let's take a look. Steps that you follow. In general, we're going to establish the xy coordinate, specify the direction and sense of acceleration of the mass center, e.g. angular acceleration, etc. If necessary, we're going to compute the body mass, the moment of inertia ig. And if the moment equation sigma mp equals sigma mkp is used, then we use the kinetic diagram to help visualize the moments developed by the components magx, magy, and ig alpha. We're going to apply the three equations of motion and then keep going. Identify the unknowns. If necessary, if we have four unknowns, we're going to make our assumptions. Is it slip or no slip? Typically, no slip or use Ag equals alpha r is assumed first. And then use the kinetic equation as necessary to complete the solutions. If a no slip assumption was made, you have to check if it's validated because we're making an assumption. We need to check if our assumptions are correct. Key points to consider: be consistent using the assumptions direction. Direction of Ag must be consistent with alpha, and if F friction equals mu Kn is used, then the friction must be opposite. Friction force will always be the opposite of the direction of the motion. And as a test, assume no friction, observe the resulting motion. This may help visualize the correct direction of friction. Examples. Example number one, we have a spool has a mass of 200 kilogram and a radius gyration kg equals 0.3 meter. Coefficient of kinetic friction between the spool and the ground is mu k equals 0.1. And then the angular acceleration of the spool We're looking for the angular acceleration of the spool and the tension of the cable. First thing is our free body diagram and the kinetic diagram, showing all the forces on there. Don't forget about the friction in between the spool and the floor. And then since this is rotating, we also have this IG alpha. Equation of motion on the y direction, well, since there's no movement on the y direction, we can use the weight to help us figure out the normal force. And it's the same as the weight, which will be 1962 Newton. And then notice that AG equals zero point 0.4 alpha, and then that is radius times alpha. AG equals R alpha, right? And then you'll have F equals MAG on the horizontal direction, plugging all our values. We can write our tension in terms of alpha. And also we have our rotational motion, mg equals ig alpha, which will be writing another equation of motion, tension, relative, another equation with two unknowns, tension and alpha. With two equations and two unknowns, we can solve for alpha and tension. Okay, next one. This thing right here, the truck, okay, where on top of it, we have this cylindrical shell carrying. This is it's concrete, 500 kilogram. And then we know the radius. We assume it does not slip on the truck and but can roll. We neglect the thickness. We're looking for the angular acceleration when the truck has an acceleration of 3 meters per second square. So first thing first, mass moment of inertia. You have Ig equals mr squared. Since it's a thin shell, we put that plug in our value m times radius squared. And then we draw our free body diagram and look at this. We have friction on the bottom. We also have, since it's rotating, we have our IG alpha. One thing I want to point out that the friction goes to the right. And the reason being, since the truck is going to the right, you feel like, well, then we have a motion going to the right, then the friction will be to the left. No. So if the friction, please do not get confused. Since this thing is going to the truck is going to the right, the friction going to the left will be down here. Okay. And then there's the friction in between this cylindrical shell and the truck. And that friction here on the floor will be going to the right. And this will be the friction force that's moving it together with the truck going to forward to the right. It's like Newton's third law, A on B, B on A. So this thing is going to the right uh, from on the separate object itself. Okay. And then next thing, we're going to write our equations of motion. We do the moment equation of moment about point A, sigma ma equals sigma mka. We have that equation with relating alpha and ag. And since does not, we assume it does not slip at A, we have AA equals 3 meters per second square. And then we plug into our equations. AG, we have our AA plus alpha cross rg slash a minus omega square rg slash a. And then we have, this looks like, again, it looks like one equation, but we can separate the I component and the j component, and then we can get our another relationship between the ag and the alpha. And we have two equations and two unknowns solving for the alpha and the ag. I feel like free body diagram over here, the direction of the friction might be one of the hardest thing to start with at the beginning. Okay, that's all I want to share with you in this video. Thank you for watching. Hope you find this helpful.